Samson's going to sing to us a variation of the theme of Yang and Yang.
Okay. I unfortunately was not very original in my title, because if you replace Yang Yang by Paganini, it was a piece by Rachmaninoff. But I think that Yang Yang are Paganini. Yang is Paganini. Oh, Hartschutz. So, but I think that at least in a topic that I've been working on my life, Yang is Paganini. So the plan I have is to say certain things of appearance of the Yang function in related to the topics of this conference. And actually, I think that on this conference already it appeared several times without being mentioned. So this, I will follow mostly the work with Nikita Nekrasov, some published recent years and some not yet published. Usually I would like to mention the previous works that we had. So we started in 1994, interested in the subject with Greg Moore, Nikita and myself, but we started publishing I think in 97. Then we had Greg Moore was replaced by Losser at some point. So Losser joined, I think in 97, 99. Then I dropped out and Nikita continued with that. So then I started doing again in 08, 09 with Gerasimov and 09, 10 with Nekrasov. So here is somewhere number of papers in the world. Okay, so enough for references. Some of the papers had funny titles like this. One was called Avatar or something like this, Greg. And now there is a movie called Avatar. The one was called Issues, and there were many issues. One was called Testing and so on. So we had some fun. And I think people in this room would agree that we had some fun. And fun continues. for some reasons. So, plan will be, I will say a few words in introduction about the role of Yang functions before I got interested in it, the way I understood them. So, there's a little bit of history. Then I will mostly concentrate on these papers Nikita and I wrote last summer. We spoke about this in January of a similar conference here, but I think today I will be speaking about that differently. Probably. And then I will continue about something more connected to Liouville. But unfortunately, I will not be able to finish. Well, I don't want to say if I know the right answers, but the connections between these subjects with Liouville. But I will say something about it, and hopefully it will be something that maybe will ring some bell for somebody. And unfortunately, for me personally, this goes even before 94. I yesterday started reading my papers from 1988, so maybe it's a sign of getting very old. When I go back to 1984, I probably should retire. Okay, so I heard about the Yang's function actually when I was a student, but it never fixed in my brain. And then when Anton Gerasimov and I started looking on computations more Nikita and I had, I was talking by phone with Leon Haftajan, who told me that this object is a Yang's function. I was written a encouraging book basically on the first page or something like that. So it was amazing that That's how it happened. And so basically, if you go to those books, old books and so on, they tell you that in a quantum integrable system, in many approaches through the beta ansatz, this object Young function is not very, it cannot be neutralized. But of course, beta equations have been neutralized all over. So the Young's function is basically an integral of beta equation. Absolutely non-trivial fact that if you take the beta equation determining allowed values of rapidities, which are denoted by lambda, so these are some equations, let's say bi of lambda equals, let's say, 0, so let me write this way. It's absolutely non-trivial that this particular equation also can be rewritten as dy d lambda I. There are many equations in one of the constant charges usually is something similar to the particle number, the number of these variables of rapidities. And if it's fixed to, let's say, equal to n, there are n equations here on n variables. But some reason this can be written as a derivative of one function of those n variables. What way we like it, sometimes they in original Young's work in 1969, they added a linear term here, so I will subtract now a linear term and I will write this is equal to integer. Okay. So in the definition of original definition of Young's, is y also contains the ordered set of integers which they call n1 to nn. And obviously if you multiply by lambda and put it there, you can put it in y, but I prefer to put like this. Okay. And as far as I understand, that paper of 1969 of Young was actually that's a paper, that's a famous paper on thermodynamic beta ansatz. And the functions they wrote was for what's called Bose-Gas, which is a particle sector of nonlinear Schrödinger equation, which is also goes under the name of Young's system. And this is an example, probably, of one of the things. So I will. You correct me if I say something.
No, that's fine.
So
can you write some equations more explicitly?
I'm writing them slowly. I'm warming up. Okay. That's a style. That's a style. So there's something I wanted to say something about Young. Someone recently showed me that by some paper by Heckman and Opta, they claim that this is one of the classical examples of Arnold's theorem, that it's called the Young system, but it goes back to Elliott-Leib and many others 10 years before Young, but eventually ended up to be called Young system. So these are the system of n particles. Bose-Gas. They call it Young system. So the Heckman and Opta submitted to Annals of Mathematics an errata. They asked to change the title of the paper. The paper was called the Young system and something. And they submitted the errata to replace the title. Okay. Some I equal j, that function j is exactly the function. So this is H2. There are other. This can be also written as a sum of something called the Dunkel operator. Where Dunkel operator can be written from that it's a step function. And of course there are HNs, which are HIs, which are some, let me call it K. K. So these are K goes from 1 to n. They are exactly n Hamiltonians. And they considered it, of course, on a circle where xi varies by xi plus 1. If I take H2, psi equals deep psi, then E has been parameterized by lambdas. There are n lambdas because there are exactly n h's. So I parameterize n energies by n parameters lambda, and then Young-Rawls equation, which determines allowed values of lambda, and proves that there is exactly one solution to this equation for fixed partition of integers. Okay? So this was what Taktajan told me in the telephone conversation.
For those who didn't listen to this conversation, so for those
You want formula for y? I'm not going to write. I can write the equation.
But there is a formula for y.
There is.
So it is.
In terms of lambdas. Okay, so you parameterize energy. This talk will never finish slowly, but let me answer this kind of questions. Okay, so there are n energies, right? Let's call it epsilon 1 to epsilon n. Parameterize them with n numbers, lambda 1 to lambda n. Okay? And the claim is, if you compute common eigenfunctions, there will be discrete spectrum, because we are living on a circle. And the lambdas should satisfy the equation of following type. Epsilon lambda j. This is product I less than j. And this claims that this equation has a potential. Oh, sorry. Don't need to pi. This is a phase. Depends on scaling of c, whatever. So the claim is that this equation has a potential. Okay? And these n's have a meaning that if you take this parameter c to infinity, so if you are extending the solution around the point c goes to infinity, then this equation tells you lambdas are basically highest weights because you get the expression of I lambda equals minus 1 to the power n. And then you can turn around. And he proved that there is exactly one solution for every solution to the equation at infinity. And the equation of infinite parameters by integers. After permutation, they will go. Okay? So the funny thing is, yeah, and this is an equation which appeared in this paper. We actually had derived that if you can compute regularized volume or some intersection numbers on a modularized space of Christian equations on two-dimensional Riemann surface, then some, these intersection numbers, regularized volume and other intersection numbers, some will go over solution of this equation, where C had the meaning of a twisted mass parameter or some kind of parameter that regularizes that volume, because it's an infinite, the volume is infinite, and that has the meaning of the mass. So that appeared, and so interesting thing about that was that immediately it became clear, since that particular case studied in this paper, as we explained with Gerasimov, fits very well in a generic picture of supersymmetric topological theories in two dimensions. So there is a, how to say that, one step that you can say that it's not only the partition function or regularized volume that we computed was the sum over the solutions of these equations, but there are also wave functions or states of this equation had something to do with quantum field theory. Okay? So what I said that sum was over the spectrum of this equation, and if you could, let's say, torus partition function, this was basically sum of 1 over this set. And the Anton and I said, well, I mean, probably there is an entire thing hidden inside there, and we had something to say about it. And, for example, we utilized the Young function as what's called effective entering effective low energy action for topological quantum field theory. So that's how it showed up, and now I want to play the game of showing you many other places where it shows up.
Which teaching system?
Just teaching equation, or what the...
Which Riemann surface?
Instead of, okay, you click the Riemann surface, you can see the connection in the one form, write the equation.
I understand that. I'm just asking, this particular Young function appeared when you were getting the volume of any
any
system,
so,
or, I mean, any Riemann surface and equal
any Riemann surface. Okay, let me give you answer.
any puncture.
Okay, answer. Consider Christian equations on some surface sigma. Okay. Write a theory which computes the regularized volume of solutions of this equation. Now you will tell me there are no solutions in this, and this doesn't matter. It's exactly the same as in flat connections. There is no flat connection on this too, but there is some quantum field theory which sets the problem. And the answer for Z regular volume, a certain function of lambda to the power 2 minus 2g, and if I would add the observables, then I will get quadratic Casimirs written as symmetric functions, symmetric polynomials of lambda, and the set lambda was going, that's the answer of our computation, is over solutions to that equation, where d of lambda is some kind of deformed one-dimension.
So do switching system without singularities on the real surface?
I don't think it matters. You just take, this question is about the set. Okay, so what if you insert the operator or put the singularity, something will happen inside.
Okay.
But the sum will go over those.
So let's see, so if you did put,
That's our formula.
if you put punctures, then there's a whole issue.
Inserting operator.
What kind of singularities you allow
Yeah,
in
yeah,
the punctures?
yeah.
Does that affects the beta on those equations? Or
No, it will not affect. It will not affect Beta-Handels equation because this thing came from integrating out lots of stuff, non-diagonal elements,
Yes.
massive things, and so on. And this you can do basically go to Coulomb branch, okay? And then the operators inserted or singularities and so on will change the measure.
I see, but not the.
Not the sum. I don't believe it will change the sum. Of course, what we did was compact Riemann surface.
The sum depends on the moduli of Riemann surface. It depends on the Riemann surface or on the topological surface.
It doesn't depend on it. Depends only on genes.
Only on G. So it's topological.
Yeah, it's topological.
It doesn't depend on the complex type.
This is not about this work.
Just one more.
I thought this has nothing to do with this.
Does the choice of the group G control how many lambdas you have?
Rank of the group.
Just the rank.
Yeah, number of lambdas is the rank of the group. Okay, anyway, so now I want to show another place for you. Okay, so this is the one place. Then Nikita and I understood actually that that's the way to think about it. So the Grassmann and I were thinking about a topological, so like that connection business, okay? So this is not this complex Python connections, each equation is complex Python connections, we fix a case, so it has something to do with it. But if you remember the way Ed Witten explained topological Young Mills being sitting inside physical and equal to super Young Mills in 2 dimensions, immediately can restate the statement as a statement about the ground states of supersymmetric gauge theories, statement about ground states of supersymmetric gauge theories if there is a good condition, which means that there is a mass gap. So if there is a discrete set of vacuum, there is a mass gap. So statements then become like this. Consider n equal to super Young Mills in 2 dimensions with bunch of symmeters, so it has a Coulomb branch and a Higgs branch, so you throw in symmeters whichever you like. Make sure that Higgs branch is massive, so you introduce twisted masses, so you have to make sure that this theory is in a good condition in a sense to discuss the question of isolated vacua, discrete set of vacua. So what are the parameters then? And these theory parameters will be the data of Higgs branch, basically matter sector, so all the parameters entering the ordinary superpotential, the set of fields, of course, because it's an equal to theory, as we were playing the games in '94, for every quiver you can write n equal to Young Mills, and so you just make it as general as you can, so that you'll be n equals to, then introduce the parameters twisted masses, 5 Liouville terms and theta terms and so on. So do as much as you can. Okay? Now I don't write the formulas for Lagrangians and so on because the plan of the talk is to review the appearance of Young functions in many different places, and most of the people know what I'm talking about. I apologize to Sasha Goncharov, I'm sorry, but I think you are only one. Sorry.
Those who know, those who don't know.
That's a joke, a Muslim joke. Yeah. There is a Muslim joke when Maulana Sredin comes to the people and asks people, do you know the news? People say we don't, so we don't know, probably are not interested in the details. Next day he comes, people decide, now we say yes, because we said no, he did not tell us. He says, if you know, why should I tell you? The third day, the people decide to split. Half says yes, half says no. He says, why don't that half tell us the other half? want to be in that situation. But everything I said here, two-dimensional, super young Mills theory, with a matter sector, with all the parameters standard, superpotential, maybe even twisted superpotential, twisted masses, variable terms, and fixed terms, and so on, is clear what I said. So, what? Ask me if it's not. Okay, so then the claim is that this theory is can be, for this theory we can write low energy effective action, and unfortunately only one term is that low energy effective action we can write. Now I will say what is low energy effective action for mathematicians if I can say that. This theory has lots of fields. There is a gauge field which lives in some bundle. Okay, so then there are the matter fields which live on some pure variety, and is there massive because I give them the masses. So the claim is that you can integrate out. The integrals are basically Gaussian up to some tricks. Integrate out everything except diagonal part of what's called a twisted multiplet or a vector multiplet, which is related. Everything you can integrate out. So there is one thing which is called the twisted chiral multiplet sigma, which contains scalar, fermion, and the field strength for a gauge field. This multiplet.
Original integral was not Gauss.
What?
Original integral was not Gauss.
No, I repeat what I said. Everything written in the Lagrange, like 6 branches, so on, you can integrate out as long as it's massive. All the corrections, the loop corrections, and blah blah, will go with 1 over mass. For example, it's peculiar to two-dimensional structures that you can write in such ways that the non-diagonal elements of gauge field will be coupled non-linearly to the diagonal. So you can integrate out the non-diagonal ones, and the answer will depend on the diagonal. So I'm keeping everything except diagonal. So it's called abelianization. Okay, this is a very peculiar, particular theory. There is a way of computing what's called effective twisted superpotential. Exactly. And by the way, it was computed, I think, by Dada, Lucia, and Di Vecchia, probably for CPM model even in 1976 or something. What year? Sometimes in 1970s. And when I showed this to Lucia, he said, "Oh, this is my problem." Supersymmetric, yeah. N equal to supersymmetric. Or who? Anyway, so the one object which is called twist effective superpotential can be computed. So this twist effective potential is a holomorphic function of this twisted superfield, sigma, which I said starts with a scalar component, which is sigma. So if I write as a function of sigma, it is the same thing. You just have to make it into superfield. So this W of sigma, effective one, is only term we can compute. Now, after I'm on abelian phase, after I diagonalize everything, so these are sigma 1 to sigma n, where n is a rank of the gauge group. Okay, and there is no ordinary superpotential anymore because I integrated out this branch. The only sigma is left. I'm on a Coulomb branch. And the statement is that this W will determine the ground state. So this W will tell you how many vacui you have and so on. And it's not difficult to actually work out the detail of this, how exactly it determines this. And the equation is,
In guarantee there's no similarities in the Taylor potential?
that's true. We cannot say anything about it. So we assume, so I will tell you what is the answer, let's say, for potential. And you will see that similarities of the Taylor potential are relevant to this question. So potential basically will be dW d sigma minus 2 pi I n I. And I have to put now this and complex conjugate here. And as Martin just said, to make a claim from here that dW d sigma equals to pi I n is a critical point of potential, we have to make assumption about G. Okay, and since we don't know how to compute it, so we say,
And what is G? What is G?
this is something which is in kinetic terms. So this is a potential term, and the G enters, it's called the Keller potential, effective theory. And this cannot be computed.
G's a
Cannot be
G's a kilometric.
Calorimetric.
Computed it.
Imperturbative expansion, but there is no concise final good formula for it that I can give you. But W I can.
Sometimes I just mispronounce it. So, the W, do you really want the, why do you need the tilde on W factor?
Well, there are two W's. There are two
Tilde
W's.
and the bar. Oh, what are the two W's?
There are two W's. One is an ordinary superpotential, another is effective.
This is the one where you've integrated all of
Everything.
that.
Yeah, so there is a tilde and bar.
Okay.
And effective.
And then the I is equal to J. And the second.
I equals what?
Great. Okay.
I equals J bar in this notation.
Yeah.
So now the important thing is what is N. Okay? So the reason you get N is because the sigma model, after you integrate out everything, so this effective action actually has a disconnected target space, which is labeled by certain integers. And to understand that, the easiest way to think about it is that the gauge fields can have monochromies, or the connection can have fluxes. So when you integrate over everything, you in particular are summing over the fluxes of a curvature of M. So when you are integrating over gauge fields in particular, you are also summing over. And now I is indexing per time of the algebra. So you have to sum over Ni's. And if you Poisson resum it, there will be another integer which actually enters it. So there is a sum over these components of Ni's, and there is an integral over trivial gauge fields. Integral over trivial gauge is not a big deal to compute actually, but there is a sum over N's. And that sum, actually, I don't know how to get into some details. That sum is nothing more but sum over in some topological language. This is sum over set of N's of exponential of N dw sigma. And when you write it as a resum it as a Poisson, or they basically write the delta function of this minus M, and that will be that integer. So I explain now what that integer is.
So, you mean these theories have infinitely many vacua?
Discrete vacuum, it can have infinitely many.
So they're rather different than CP1 sigma models.
Oh no, this is what I just said is very generic. I said if your theory has a discrete set of vacua, okay, has a massive Higgs branch, and you're in a good condition that you can abelianize, okay, what you will get will be this. Okay. So now there is some doubling, and in each model you have to compute it. So depending on the model, you might end up the theory which has discrete set but the infinite set of vacua, or get a finite set of vacua, because now set of vacua are given by critical points of this potential, assuming what Martin was asking me, we don't know anything about Gij, but we assume that only critical points are here. So then we get the equation dw tilde effective d sigma I is equal to pi I n r.
But the choice of n can depend on the t, or arbitrary law.
N's are arbitrary at the moment. It might happen that this equation has solution only for particular n's. I think that some example that Beston was discussing was had a solution probably for only n equals 0.
Okay, so it can happen that only for a finite set of them.
Oh yeah. And then you have that finitely many solutions. Because when it's written for every integer, and this is a rank of the gauge group times an integer set, okay, there is equation. So that determines sigma in terms of n's. Okay? Now I want to rewrite this. Sigma is the scalar expectation.
Why you do not have solutions?
No, everything is complex here. Sigma is complex.
Yeah, so how it can happen if you don't have solutions?
Okay, so the next step. Okay, next step is now. Okay.
Samson, sigma, I will love it. Sigma, I will
Well, they're not yet. This equation and this cannot be yet identified. They look similar.
identified by your arrow.
Now I will claim. Yeah. Now I will claim.
Like identified, you put an arrow.
Yes.
My talk is designed as a conversation. So, answer on this question is Now I will, next thing I will say is that lambda, this is coincidental at this moment, that I will present, I will claim that there are examples I know when y is equal w when sigma equals lambda. Okay? So this can be coincidental or something very deep set. Okay? So this is a topic right now. So I'm showing you another examples where actually Nekrasov and I did hard work to cover every example I would get from you or Spianin or anybody. So I was collecting examples for y in quantum integrable systems, and we were trying hard to reproduce it by presenting the gauge set. Okay? So I think it's fair. I mean, arithmetical, simple, elementary, mathematically, it's a simple thing I just said. There are some functions coming out of supersymmetric gauge servers which are called twisted effective superpotentials and Coulomb branch. And the vacuum are described as critical points of it. And there are another functions coming in a quantum integrable system, which are these Young functions, and the spectrum is determined by critical points of that. So Nekrasov and I claim that for every known quantum integrable system, where the beta equation is known, there is n equal to super Young-Mills theory in 2 dimensions, where I can specify those data, and now the Sasha program can get into the talk back. Now we're specifying some data, where these equations coincide, actually coincide without any filter definition, because if there is a filter definition, goodbye. Not interesting, because 2 functions up to filter definition are basically equal if they are same variable. But they actually coincide. Okay? So, example, right. So now I will write this W tilde effective of sigma and y of lambda. By the way, in this room actually are, I think, the world experts of this and world experts of this also. So I mean, Martin knows everything about the twisted masses and all this kind of what this thing is, and I think Leon knows everything about this and many others. So now I claim I want to give you one example, at least one sexy example. Okay? Okay, let's consider n equals 2 super Young-Mills, where X branch, so with the gauge group UN, so I take now gauge group here to be unitary okay? And I want to add to it L, which is some number, fundamental representations of this gauge group, and denote them by letter Q. So I have QA, where A goes from 1 to L. I want to add to it also L anti-fundamental representations, and denote them QA tilde. Okay? And I want to put 1 adjoint representation, and denote them by phi. Okay? So this is my Higgs branch. Well, it's the simplest query. So claim is, yeah, and now the global groups, if there is a global symmetry group, so I can give each of them twisted mass, which is some complex number. So I will make this guy with an F, A. This guy will have twisted mass M, F bar A, and this will have twisted mass M adjoint. Okay? That's some complex number. So Lagrangian is specified now. Any questions about it?
Do you put in a trilinear?
I can put trilinear potential also. That I will put in a second. Okay, not yet. Because at this moment, this is enough to integrate. This is enough to write W. Okay.
Why do you call this twisted? These are ordinary masses.
No, they are complex. They are twisted masses.
Samson
There is U1 to the power L.
They enter the critical potential, not the slow potential.
Pardon?
They
Which
enter the
corresponds to twisted mass?
potential.
Okay, I think if X is a, someone has to correct me, if X is a chiral superfield, I think twisted mass is U multiplied X bar exponential V, where V is M theta plus theta minus bar, I believe, where M is this mass. Okay, and then you have to put here, you have to take your representation where the Higgs branch lives, decompose into additionals. So you write as a sum of mi and ri, where ri is irreducible representation. So your representation where the big branch lead decompose into the irreducibles. Okay, and the twisted mass is now.
Sorry, you lost it. So R is the representation of UN?
No, R is the representation of UN flavor.
UL.
No, UN. You take a representation of your age group. It's a color. So it's a representation of color group, and the up doesn't have to be reducible. You can put
Yes.
with multiplicities, right?
Good. Okay.
So twisted masses will be living here in cartan of UM flavor.
The rectangle. It's up, right?
Yes, that's a
There is some. There is some. And the twisted masses will be living here.
in the Cartana.
In order to preserve supersymmetry, they have to be in cartan in order to preserve supersymmetry. And I think formula is here. Now I have to write what? Identity times.
So,
No, it's just the usual 5 bar e to the 3.
You imagine
where it's
gauging,
easy.
yeah, you imagine gauging it.
Yeah.
You imagine gauging the flow of symmetry, and you.
Absolutely right. So you make a gauging. This V
Yes,
has a,
and
of
you
course.
imagine gauging it, and you turn on the scalar.
Why am I wasting time? Okay.
Because I asked.
Oh, sorry.
I
So,
asked
but
you to write down
important,
the term of
it is supersymmetric only if M's are in cartan of U. Okay. That's clear. And they are complex numbers. Okay, now so for this particular theory, claim this equation coincides with XXX spin chain beta that if now XXX spin chain with spin S is on each lattice of the length L, if there is a relation between these parameters, so I have to now parameterize these parameters in terms of parameters that you have in spin chain. M's, yeah. And there is a formula for that, and that formula has explanation, which is the answer on the question Martin asked just 2 minutes ago. So relation between those parameters in the ordinary, so you have to connect completely, MA of F has to be minus mu A, which is called impurity on a side A in the spin chain. SA is a spin at side A, U, and U is a coupling constant in there. Similarly, MA F bar has to be mu A minus. There are spins of different sides, length L, everything most generic, all impurities turned on, times U, and M adjoint has to be I times U. So these are relations between parameters, okay? And these parameters are only allowed parameters in the gauge. So in general, you can have any parameters in gauge. It doesn't have to be this condition, okay? But it's are only allowed ones if you add ordinary superpotential for this matter sector, okay, to be sum of terms like QA 5 to the power 2 SA QA with some coefficients. Okay. If you add this kind of term, where SAs are half integers, this is a valid term. Okay, what Martin called trilinear, but now he's playing with BlackBerry. So if I add this term as a trilinear, now it's not trilinear because S's can be higher, then this will be only allowed masses.
And U, what is U then?
You arbitrary complex
Yes,
mass.
the scale.
Yeah. So you put it to 1 usually in spin chain. So this is a scale. So claim is that this equation for z value of those values of parameters, okay, is a beta equation for this system of spin chains, which is written in this form.
So I'm not very familiar with XXX spin chain. Could you
XXX spin
tell me a
chain.
little bit more what those parameters are in the spin chain?
David, with all due respect, maybe I tell you in private, because I want to get to my talk. I mean, this was just, how to say, to show that this is a big picture. I mean, it's not just little. So these parameters enter as impurities in a spin chain Hamiltonians. There is an opportunity to put some magnetic fields, whatever. So lots of stuff in spin chain Hamiltonian, and these parameters are there.
And so mu is the magnetic field, and let's say mu A was
S is a spin. U is a space
S was a
parameter.
spin. Okay.
I will be talking about something that you will be talking about.
So, but is this relation between all eigenstates?
Yeah, so the claim is that this is only vacuum eigenstate.
Is there anything special for, let's say, vacuum paramagnetic or antiparamagnetic vacuum?
Okay. The first statement is that these are only ground states for a supersymmetric point of view. So these are only ground states. They correspond to all states on a spin chain. As you know very well, something special happens in a spin chains when some parameters take special values. Very interesting statement is that exactly in that places we can see that something very special happens in a gauge cell. And for example, if you remember when mu's are aligned, like shifted by 1 and so on, you have the generator representations in the Youngian theory, and they correspond to some opening up a new branch in gauge cell. So there is a... Okay, so now I think I explained everything about two-dimensional gauge theories with fixed branches, arbitrary fixed branches. Because I mean, some long paper and that I still have not published has every example known. Unfortunately, it is case-by-case study. No, if there would be some general big theorem which connects these things, it would be beautiful. But at the moment, you give me a supergroup, or you give me a Hubbard model, you give me this, we will give you what has to be Coulomb branch in the Higgs branch in the gauge cell.
What about Sinch-Gordon?
That's interdimensional. So very good question. We don't cover models like Sinch-Gordon.
In your paper, there is a statement about it.
What?
You can cover Sinch-Gordon as well as the X6.
You see, if I cover x with the spin, then I can limit it. I don't
No
know.
way.
So those all statements are not correct. Anyway, this is about spin chain. I made very specific statement. This is about spin chains. I had a question whether there is a finitely many solutions or infinitely. This is a finite dimensional space of solutions here. So,
You do X, Y, Z spin.
okay, I'm going step by step. I just said that I want the statements to be understandable, but not. This is not a Gelfand kind of thing. No, when I worked for a couple of years after my PhD studies, because I was out an immigrant inside. So I worked in a nuclear physics institute for a couple of years, and there were seminars by Liouville. There, until everybody in the room understands what speaker says, seminar doesn't end. So this is not that kind of seminar. So it was at 11 and
Was
finished
that
at
solved
8.
sometimes by ejecting someone from the
So if you understand, you can leave.
No, I meant someone who...
Natural understood everything.
Story about Samson when Edwin gave a talk. That was the famous story. And here was
Oh, that was Politzer. Yeah. He gave a lecture on his famous work, and Gribov said that all this is wrong. Usual story is that everything is wrong. And then, oh, no, it's not wrong. About half an hour later, it is correct, but it's trivial, not interesting. Half an hour later, oh, no, we are sorry, it's not trivial, not interesting, and wrong. But we already know all this. And half an hour later, well, we don't know all these things, but we don't need to know. It's like that. And 8 hours later, if they say, well, good, then good. So Lipata was a champion of these things. He would come with a bottle, nice bottle or something. So I went through this. And I can tell you, they tell me Politzer gave a lecture in 1975. And Gribov told him all these stages. And in one stage, Politzer just left. So Gribov was giving a lecture instead of Politzer for 2 hours. They didn't notice Politzer. He was gone. And then they got a call by KGB saying that your American speaker is sitting on a tree somewhere. He's not allowed to be in that building. So they start looking for him.
You're not referring to the famous line from Shrek when you say he's sitting on a tree.
Well, this is of course my, how to say, my exaggeration. But they found him some other building.
No, I understand, but you don't know that line from
Of course I know the line from Shrek. When I make my exaggeration, probably unconsciously some things come from the many different places. Okay.
You know that.
So can I continue now? Do I have permission? Good. Okay, so another interesting, by the way, before I say something else, the formula I like, that some of the people in the room would like, is that if I think about topologically twisted theory, okay, in two dimensions, then I don't talk about the ground states of supersymmetric physical theory, but rather I'm talking about a complete topological filter, because these two sectors are supposed to be equivalent up to the subtlety of the singularities in a Keller space. Okay? Keller metric, suppose Keller methods have a singularity and so on. Topological theory knows as much as the ground state. So then the topological theory now has to be written in terms of these fields, because everything has been integrated out, right? So we have to write now the topological theory, abelianized topological theory in terms of these fields. And the statement is, first statement, everybody knows about those theories. In this what's called the triple, what is this? Triple field representation when you have sigma, psi, and engagement. Some class. You had a review paper. So these are the fields, and there are abelian. And then the claim is that if you are given a function, let's call I, of sigma, you just have to descend twice in this, and you have, of course, the Q and everything is given, descend twice and construct the two observables. Okay? And this would be the action of topological theory. The claim is that if you start with a joint invariant function on the Cartan, any function, you will have a theory. So the trick is to compute this function up when ultraviolet theory is given. Right? So this I is actually double. And the action, that action is dw d sigma times that plus d2w d sigma squared side side. That's all. And when W is sigma squared, which is a case of two-dimensional Young-Mills that we can take, that this is nothing more but sigma I of I plus psi psi topological two-dimensional Young-Mills. So W equals sigma squared just corresponds to something everybody knows. So what happens when we do our stuff, we just compute corrections to this. Because for every W there is a topological theory. So we identify this W.
So you're still in the two and equal two context.
Yeah.
Two common two context.
For supercharges.
Right. So you still know what an auxiliary field.
I integrate up to it. So I reduce it to this. What the claim is that see, you start with something in ultraviolet theory, and the claim is after topological twist, you can now go to the abelianized theory, which is a standard procedure of integrating out stuff. Right. And whatever you will get will be this Lagrangian with summed up. Of course, there will be some kind of dilaton term also, which is Q invariant always, which is this measure factor, d lambda to the power 2 minus 2g. But whatever you do in this theory for supercharges, you will end up with this action with summed up.
I'm still confused because naively I would get, instead of f, I would get f plus id.
Integrate out all this is
But if I integrate it out, it seems to set the thing to zero. It seems you lose everything.
Well, it's probably to think about the superfield formulas and so on. What I say I have a joint invariant function.
I mean, should I really think what you had before that you wrote?
I have d and I integrated out this.
Okay, so I really should think about the square root of this.
Yeah, okay. Well, you don't have to, but okay. So the claim is okay. Let's say this way. In this small set of the fields, I don't know how to write in superfields immediately right now, but claims that every adjoint invariant function of sigma produces Q invariant Lagrangian
Yeah, sure, no, of course, that's
And
true.
the claim is, and why it's correct and so on, is a separate question, and I want to move on with my talk because now I want to move to other dimensions and so on. This will be Z, okay, topological edge.
That's
And
what
that's
I
the
mean.
reason why the dWd sigma is integer is the set over which the sum is going because F has a flux. Okay? In two-dimensional Young Mills, this is sigma here, and sigma is an integer. Okay? And these are the highest weight representations that we can get into dimensional Young Mills, where we compute passing sum over all highest weight representations with some measure. Now they are replaced by these things that I just wrote. The critical points of that. Now anyway,
No,
now what?
I'm sorry. I'm sure this has a simple answer, but I just want to know. So if you literally do the calculation you described, you don't get that. You get F plus ID, where D is an auxiliary.
Okay, so now F is dA in that case. Here F can
Yeah, F, I know it. F is dA, but you have plus ID, where D is an auxiliary scalar.
right. So now D can have a flux, but F has integral equal 0.
No.
I'm sorry. I just what I say is this. Everything
One is,
can be.
you know, one's the imaginary part, one's the real part. One's a scalar, one's
This is a contour integral here. It's complex. Yeah, I understand what you're. I think I understand. The action is Z plus T of something, and everything which is non-holomorphic is here.
Integrate out the quantical fields, two Hamiltons and two bosons, and the auxiliary with Z together with sigma bar, which
So this is a bar also.
So this is a 2-0 formula?
Can I move to the 4 dimensions and keep now 2 questions? One is Martin questions I owe you the answer, and another was what was I think other question.
Now this question when it's switching.
Okay, that was the question. Can I move on to 4 dimensions now, please?
Okay. Sorry.
Okay. 4 dimensions. So now, yeah, other dimensions. In order to get the spin chains, which are not of the simple type and so on, you have to discuss stories in 4 dimensions and 3 dimensions. So you can take a 3-dimensional supersymmetric gauge theory and consider on R2 times S1 with some radius, let's say radius of this to be R, such that when radius is 0, which means a dimensional reduction, you get in a previous story. Okay? So now you can ask the question, what happens here in this supersymmetric gauge theory? An answer is these guys correspond to the same setup, same field content I just gave you, and so on, will correspond to XXZ, where the radius will be related to inhomogeneity, anisotropy of the XXZ. Okay? And this theory, since the radius is a standard story, since radius is finite, we can treat as a 2-dimensional theory with infinitely many Kaluza-Klein modes. Okay? The Kaluza-Klein masses are twisted masses because now we have a global symmetry of Z. So we integrate them out. We are in the same setup as before. Just we have infinitely many fields. So the Lagrangian, instead of the previous Young function, had some logarithm. When I wrote the equation, it was clear that there was some logarithm. So now that logarithm will become dilogarithm because I have to shift by integers, which are Kaluza-Klein modes, and sum up, and it will become dilogarithm. The Young function now is a dilogarithm generalization of the Dirac and so on computation, which had logarithm.
Oh, so the Young function is this finite sum of classical dialogue.
Just it's a classical dialogue. I mean, it has an
sum of
sum of classical dialogue. Like Venetian-Yankelovich potential, which was before in 2 dimensions, it's a Venetian-Yankelovich basically. It's all to Dirac and others computed. Now it gets transformed, takes that sigma log sigma, shift sigma by integer, sum up, you get dialogue. So now suppose I want to go to 4 dimensions, I can do the same thing on T2, right? So I consider R2 times T2. The claim is that the beta equation I get this way will be the one that written by Taftajer-Fadeh for XYZ. Or sorry. And there is a Young function for it, and you can write the same trick, you can do the same thing, but there is now lots of stuff you are getting, because you know, now you can turn the fluxes, you can introduce B field on T2, lots of stuff you are getting, lots of parameters. Okay? But that 4-dimensional theory, you treat again as 2-dimensional theory, integrate out of the Kaluza-Klein, and the claim is that you get XYZ more general. Okay? So now, this is not very, I mean, when we were doing all these kind of things, eventually, I mean, there are so many of those integral models, we found a complete equivalence of those to the vacuum sectors or topological theories with 4 supercharges, and it started becoming boring, so we decided to start considering the theories which are not of this type, which are not given as a finite dimensional quantum system, like these guys are, but are given as a classical mechanical problems, and you are asked to quantize.
If you start with the 4-dimensional case, it looks like in some limit you should be getting things that are related to good morning.
My talk is supposed.
It should be the other way around.
It's the other way around, yeah, but it's the other way around. But my talk is supposed to finish saying something about that.
Okay.
And actually, I hope very much something sexy about that. And I'm not sure I get to that point. So, what? Well, this word doesn't mean the word that you might have had in your mind when I pronounce it. Every sentence is understood on the level of intelligence of the interpreter.
Of course, if you use that, you don't have to say anything.
Okay, I want to say something actually interesting. So let me go. Okay, so now I want to consider cases when the system is given as a classical integrable system, and I want to quantize. And the first thing comes in mind immediately, because in 2-dimensional super-Young-Mills in 4 dimensions, we already have such connection. Okay, 2-dimensional super-Young-Mills. For n equals to that's what happened when you are distracting me with the question. Well, this workshop, actually, good things about these workshops are that, especially the January one, the previous one, is that we can communicate. So I don't mind all these things, but I really want to get to the point. So n equal to super-Young-Mills in 4 dimensions has continuous moduli of vacuum. So it's a manifold about which we know everything, many things. And this, by the way, all kind of measures and so on, I don't specify at the moment like the sector. So this kind of theories, we know that they have V described, this is a moduli space of vacua, described by algebraic classical integrable system due to work of Gorsky, Machakov, Morozov, Krichyver, and there is one more M, Miron. And later by Gennady and Witten, and many other work. We know that this underlying geometry here is this, and as far as I understand, the Krichyver in this particular paper was the one that for the example that I will be talking about, which theoretical Moser, he had in 1979 the notion of the prepotential. What was this? What? Luxembourg, but he also had 80. Okay, Luxembourg. But I also thought that, no? People working on monopole moduli spaces kind of prepotentials around that time, probably. No?
I mean, the first paper I know, the potentials are given by Liouville and by Gates.
Anyway, so this we know, and the idea then immediately comes that if we somehow can utilize this theory to be 2-dimensional with 4 supercharges, right? Then we can run this theory. So we have to do something. I know. So this is a theory in 4 dimensions with 8 supercharges. I want to somehow convert it in do some procedure when it's effectively 2-dimensional with 4 supercharges. And then I can run my Young function business. Okay? This is supposed to be variations on the theme of Young.
I mean, presumably having extra supercharges doesn't spoil it, right?
Having extra supercharges sometimes, I mean, for example of Hitchin system I started with was n equal 4 with masses in 2 dimensions. Okay. So it had 8 supercharges and there was a mass there. But something happens here which is important, I think, conceptually, and I don't think, when we wrote the paper with Nikita, I don't think that this was kind of captured by people I've been talking about. So I want to explain what is it. So now, the question is that we want to study two questions, actually. One question is quantization of these classical integral systems. And another question, we want to study deformation of four-dimensional n equals 2 such that it's effectively, it's a low energy effective action. It's doing it. Because if we cannot connect the deformation that effectively is two-dimensional with the quantization here, I mean, we can be in a business, right? I mean, and the hint to this being possible is the fact that in this system, this algebraic classical integrable system, which was very well reviewed by Andrew yesterday morning, and I don't think I have to go there, there is a notion of two types of action angle variables. I will call them A and AD on base of that vibration, which was on the blackboard here. You know, there was degenerate torus. I will not. Imagine.
B is not B.
B. Actually, B prime, because B degenerate. So A's and AB's, which were periods of actually PDQ on that classical integrable system, is a 1-4. It doesn't have to be Seiberg-Witten curve. Liouville 1-4. It doesn't have to be Seiberg-Witten curve. Liouville 1-4. You take Liouville 1-4 and write that A to be integral over A cycles. And this is now different lambda. Don't ask me why this lambda is the same as rapidity. This is the one, Liouville 1. Liouville. It's very important that we are given this thing. Why don't you like it? Don't interrupt. Okay, and AD would be over B cycles. An important thing here is that the fibers here were algebraic, polarized algebraic varieties, so they had this scalar form 1-1 form, which defines canonical pairing of A and B cycles. So the only restriction was there. And we had this, right? But since these are, usually if it would be the real integrable system, not complex, but real, okay, then we have only one of these, because according to Liouville's theorem, the fiber is a torus, real torus. So we have one of them, and they are called action variables, and angle variables are the angles in the fiber, right? But now we have twice more of them, and as you know very well, if you write this auxiliary space of ABs and A's, the relation between these two defines a Lagrangian submanifold with respect to the ordinary symplectic form, DAD, DA. Holomorphic symplectic form. And that means basically that AD is dx, a derivative of some neuromorphic function, which is a half of the variable, let's say x, and introduces this preposition. And so that's naturally. And the claim of the people here was that this is the same f as in Seiberg-Witten. And now, according to what we were talking about, we want this to be a classical meaning of the hour quantize. So now I'm saying that f, prepotential of this classical integrable system, should be classical limit of my Young's function. Okay? So now, in this kitchen that we are sitting right now and trying to figure out how to do this thing, we know one thing, that df, so there has to be some Young's function y in this kind of new series. It has to be something that happened here, such that it is f divided by, now I will call the Planck constant by epsilon. Okay, don't want the complex number epsilon. So it has to be f divided by epsilon, because I plus finite, and epsilon goes to 0. Because I want to interpret the equation df dA equals AD and equals epsilon times integer as kind of orthogonal. So this is the way we start thinking about it. So we had this equation. Young's function, which is f divided by epsilon, its derivative over the Coulomb moduli should be an integer, right? So df divided by epsilon dl is AD. But AD has to be an integer because that's our quantization condition that we were talking about the function. So somehow it looks like that we are writing the theory in double variables AD, but quantizing wave functions are written in variables A. Okay? So let's, because AD is like omega, I had this Lagrangian before, dw, dA, and blah, blah, blah. So that's kind of mentality. So now I have to hook up this theory, and we knew this theory actually from previous work, because now I answer the way I wanted to think about this quantization, and I will present the answer. And the answer is, consider that theory on R2 times what Nikita calls now omega background. So omega background would be 2 epsilons here. So make one epsilon 0, call this epsilon, and consider that theory on this manifold. Now what is the property of the gauge? It has a Lagrangian, by the way. It has been written in this ODS probably many times. And I'm told Nick Russell is giving some lecture course on this kind of thing here in Stony Brook, so I won't get much of it. But that theory has a property that it has two-dimensional super Poincare invariant on R2. So this epsilon breaks. So if I have both epsilons, then super Poincare is completely broken. Actually, from SU2 subgroups in Moret's group here, only U1 subgroups are equivariantized by this epsilon. So this rotation with angles of epsilon, if I have one epsilon only, gives me the theory localized on second R2, which has no epsilon. Okay. So it is a very nice version of Kaluza line, if you wish. That's my understanding after thinking about this and talking to my previous collaborators and current collaborators and so on. The best way of this to think, Kaluza-Klein type of construction, when instead of expanding all the fields, let's suppose Z is the second guy. Okay, we have Z1, Z1 bar, and Z2 bar, and our rotation is a phase rotation with epsilon of Z2. Then you are thinking instead of Fourier expansion of this field, which is a field in Lagrangian, rather keeping Z1 like that, introducing the labels for expansion in powers of Z2, because that's how charges will be according to that rotation with phase, right? Now they will have charges as associated to this label F, because epsilon rotates Z1, Z and Z bar in opposite direction. So now this is sum over LL bar, and to make it convergent, you put Z2 bar, some kind of convergent thing. And this is instead of Fourier expansion. And only labels of 0, 0 will be analogous 0 modes, where the theory will be massless.
Can I actually think of it as compactifying on cone?
A bit probably, but this compactifying cone has this problem that it has singularity. I mean, this one, what happened here is that everything lives in the tip of the cone. If you wish, in that language, everything lives on the tip of the cone. So all the guys which are labels more than 0, they will have masses. So they are they will have like Kaluza-Klein masses, which will be twisted masses in two-dimensional language, and we integrate them. So this is a theory which is a two-dimensional effective. Basically, Laplace operator acting on this guy will have a mass which will be some kind of difference of these charges plus the twisted the mass of original theory if there was a mass, and things like that. So and of course an ordinary gauge charge like A lambda AL minus AL bar, because a gauge group has a joint representation. So it has all of these guys are massive except the lowest guy is when L's are 0, like exactly like in Kaluza-Klein.
Does anything special happen when epsilon?
When epsilon is 0, this is all completely small.
No, not when epsilon is 0. When epsilon,
Integer, 1 over integer, or
Epsilon is the dimension of mass.
Dimension. So it's either 1 or 0, or you can scale it to 1, 0, infinity. So, no. Okay, so now this theory then, now I argue that this theory localizes on a fixed points of this rotation, which is entire manifold R2. Okay? And now I can tell you how many supercharges it has. 4. Right. So now I'm in the setup of my previous talk. Okay? So I have to compute now the twisted effective superpotential of Coulomb particle. And we did not even have to compute because I give now two formulas which makes everything clear. So one of the, how to say that, I was talking about all these works that we've been doing for so long. One of the achievements of those work was that we actually used those parameters epsilons as a regularization of the integral of moduli space with instantons. For example, with Greg, we even proved some bound state being correct to rank theory to exist and so on. So these epsilons were very important to regularize those integrals. And at some point, Nikita, Andre, and I even wrote some conjectural formula with epsilons which would test hypergravity. So now, since Nekrasov already used that formula to prove, and many other things, to prove hypergravity, we decided to test now that thing for this. Okay? So there is a formula which works on the lowest order. This term is correct. Okay? It reproduces everything. This is Nekrasov's result. So we try to test it now to the next level. And that is, so if Nikita 02 was taking log of partition functions, which the function of epsilon 1 and epsilon 2 and all the other parameters, multiplied by epsilon 1, epsilon 2, and take limit, okay, we decided to just little modify this. So in some last summer paper, we take limit epsilon 2 goes to 0, epsilon 2 times log of the epsilon 1, epsilon 2, epsilon 1 equals epsilon, and call it WA epsilon. Okay. That thing, according to previous formula, does start with f divided by epsilon and the final terms. Okay. So first claim is that the W is effective twisted. This W is effective twisted superpotential of that theory on R2. Second claim is, if this theory is n equal to star, which means n equals 2 plus massive adjoint, which actually, if the mass goes to infinity, also gives pure n equals 2, and which actually allows also to go to 5 dimensions and study 5-dimensional theory. So there are many models here covered now. Then this guy depends on Q, where Q is exponential of I tau, and tau is what theta divided by 2 pi plus I over g squared, something like that. The coupling constant, and it doesn't run. Okay, this is a theory where this guy doesn't run. So this is explicitly depends on Q, right? So now, going back to the classical integrable system, the classical integrable system for this theory has been identified. It's called elliptic Hologger model. This is n particles. I don't write now the function. N particles interacting with Weierstrass function potential pairwise. And Weierstrass function potential is a double periodic generalization of 1 over x squared. This model had never been solved. And it has, of course, elliptic parameter, which very easily can be matched with this Q. Okay. So claim is, since that equation for an elliptic Hologger model, which is sum over minus b over dxi squared plus this mu times mu minus 1, this is what we would call m squared in the gauge theory. That's we parameterize that way to match the one thing times the Weierstrass function, xi minus xj sum over n equals to. So spectrum of this operator, L2 spectrum of this operator is not known. Right? But what we can do is consider this potential as periodization of 1 over c squared. So that P then will be this plus an e to the power n, where Q will introduce a real period. So this has imaginary periods, h squared is imaginary And Q, then I will take exponential of minus beta to introduce a new period, which is real period. Well, that would correspond basically what here I'm watching the theta, the expansion. Theta, no, sorry, that's G, theta equal to 0. So the claim is that this one is easy. This is hypergeometric equation. If I turn off the Q, so which called the perturbative part. Right? So one of those things we have has two solutions. So one solution behaves for small x as xi minus xj. So by the way, there is an affine Weyl chamber here. I can actually go to the affine Weyl chamber and sit inside the affine Weyl chamber and watch only, let's say, two x's, xi minus xj. And there are two solutions. One is this, another is this, at 0, when I approach the wall, xi equals xj. Okay, there are two solutions. So claim is very specific what we do. We take this solution only for this hypergeometric equation, 1, the new one. And new is more than 1. New is more than 1. Sorry, new is more than 1. It's very important for the next part that I want you to talk about related to the other things that I'm not getting to. So we take that one and then perturb it in Q. But define for 1 over sinh square x, the Yost function and asymptotic momenta to be parameter A. So that's defined. This guy, this hypergeometric equation, you know, the Sattler property, this is lives on infinite line. There is a notion of the incoming and outgoing waves. There is a notion of asymptotic momentum. And Yost functions are perturbed around that exponential of IPX. Okay? So the perturbation is in Q. So now what I claim, that we verified with the Grasso, was that if I call Z asymptotic momenta to identify with a Coulomb model, which I called it, it's very important to identify right coordinates. Then this equation, dw, this Young function, also formally expanded in Q, but exact on epsilon, of course. There is no expansion here in epsilon. Exact on epsilon, but formally expanded in Q. To the order like 6, or what was it, 6 order in Q, will match the spectrum of perturbation of the elliptical Lagrange model around 1 over sinh squared. This is extremely non-trivial statement, you know, because this model has not been solved. So claim is that that particular solution perturbs, so you're right, psi equals solution equals psi 0 plus cube psi 1 plus q squared psi 2 and so on. And a perturb, and on each order in Q, you write the spectrum equation. Because of this is a wall, I mean this is a sinh square, it has actually discrete spectrum in each order, it matches the equation. So we declare it as a solution to the elliptical Lagrange model problem and all the problems related to it, which are including the periodic Toda, which includes Rusinaz in 5-dimensional theory and so on. And now the third topic of Young function was supposed to be Oper. Okay, I wanted to go to the other example, and now we're hitting the conjecture of Aldai, Gaiotto, and Tachikawa, which says that the case, so this corresponds to the Hitchin system with one puncture on torus.
5 minutes.
I can. This corresponds to the Hitchin system on a torus with one puncture. The first example that I think that Aldai, Gaiotto, and Tachikawa, they actually had this example also. Okay, they had this example. Its matching is difficult there. It was NF equal 4 theory. So NF equal 4 theory corresponds. Well, SU2 NF equal 4 will be what? A sphere with 4 punctures, right? But I can consider SUN NF equal 4. Or NF equal 2 and C. Okay, so I want to consider now those class of theories. First statement is identify this algebraic classical integrable system. Okay? So this is NF equals 2 and C, or for NC equals 1, NF equals 4, and NC equals 2 and NF equals 4, which should be the sphere with 4 punctures. So I have to identify ACIS, and then unfortunately, Nikita and I spent some time to figure out was there a clear statement in literature what is algebraic integrable system for this guy. And we settled on the one statement, which might not be the one that everybody in this room. Okay? We declare that this is SL2 Gaussian. Okay, so I have to say what is the classical algebraic integrable system, and SL2
It's a
Gaussian.
definite tension system.
Yeah, but now we're okay. Okay, so this, let's say this way. Under some line of sorts, you end up with equation where Hamiltonians are sum over A not equal B, delta AB, dA minus dB, sum is over B,
This is SL2 Gaussian equation.
and delta AB, yeah, is EA FA plus FB, FA B, plus I think is 1/2 H. Where E, F, and H are differential operators acting on the infinite dimensional representation of SL2. Okay, so let's say E is like x squared, xa squared, dxa minus lambda x. You know how to represent SL2 generally. So it's a physics analogical equation. Critical level of physics analogical for SL2. Okay, so now this replaces for us our Calogero system. Actually, this is for algebra, but if the wave function, I have to say what are the wave functions. I gave you only operator. I was clear. Let's get SL2R. But it can be SL2C also. It can be SL2C, and then I have to pick the slides and so on. Calogero was also a real equation, but I complexified it. So this has to be it, and this has to have a Young function, right? So after being quantized, this has to be a Young function. I wanted to say something about this Young function in relation to. Okay, so this has a Young function. Now we also know this conference is called Liouville. There is SL2 operators that don't have to okay, and this. After certain Fourier transform, after a certain game of this is related to SL2. There's a one-to-one relation between this and SL2. As an operator, I emphasize, as an operator. I did not say anything about what kind of solutions I'm looking at. An SL2 operator is related to the Liouville.
This is all for SUN?
This is SL2 now. I'm starting.
Okay, so this was a square plus T.
You know everything. There's
No,
nothing
I
to
don't
ask
know,
here.
actually, I don't know.
We heard the Taptajan's talk. We heard Nate's talk. We are hearing now my talk.
I'm
And
sorry.
we combine all these things and so
It's just
on.
that there would be, so now it looks like equivalent of SU2 gauge groups other than SUN and equal to 2NC, so I was trying to understand if I got lost at some point.
No, I'm
or
talking
if you
about
just changed the theory.
SL2. This has, of course, SLN generalizations. I can go to the, but this is SL2 Oper. This is a Liouville, and Taptajan explained that Liouville, that Oper is related to the Liouville, but very tricky relation, by the way, emphasized, very tricky relation. And I say SL2 Oper is connected to this. Now I want to make
How many ZAs are there?
these,
Yeah. It's a sum over B different from A with the range of B.
there are n of them. There are,
So this is not a SU1 equal to 4.
oh yeah, well, 4. NF equals 4 would be 4 Z's. I said this.
But this is the generalized.
And this is generalized. Well, I said sphere with 4 marked points will be SU2 NF equals 4. I want to study now sphere with n marked points.
I understand.
Okay, so let me go. So I want to make some statement. Okay, so now this guy who is connected to Z is connected to Liouville, but on each step of connection there is a trick. For example, Leon Taptajan very clearly explained that not every SL2 oper is giving a solution to the Liouville equation. Right? The connection to SL2 oper, this also is very, very seriously connected to in what class of the functions I'm looking the solutions. And this now I'm going to find the common eigenfunctions of this. This is now SL2 representation, sir. The practice with conformal blocks and from childhood is that it's conformal blocks actually always one representation there has to be projected. If you remember, when you study conformal blocks, you have n-1 representations, and the last one somehow is an intertwiner. So you can study the product of representations and start taking wave functions to be symmetric functions on the tensor product of representations, or instead of that, study intertwinings, like let's say for 3-point function, one representation into two. And the Moore library, for example, we're playing with these games, looking on the properties of conformal blocks under. But this is not a conformal block, this is a finite dimensional SL2. There is no Kac-Moody. But similar questions arise here. What is a space of functions? So we have to specify that. Okay? Then we have to specify the solution and define the Young function. The claim is that if I for a second discount the relation to Liouville and study SL2 order, there is a notion of Young function. It was, by the way, a dream question about a couple of years ago for why not these people who were doing better answers just instead of studying the Baxter equation and write better answers and so on, also in addition to it, tell me general definition what is Young function. Okay. Somehow give me one word, like classically it is like this, and we know what it is classically, Young function. And then quantization is like Drinfeld said, that you have this Poisson group, and then you have a Hopf algebra. And quantum group is a triangular Hopf algebra. So this word kind of is missing. So for Young function, we don't know if I give you classical Young function, how are you going to get me the quantum? But in algebraic better, that if I give you classical R matrix, you know, there is so that word is missing. So I was dreaming about that word. And I think that Nekrasov and I, and we talk a lot with Leon, as usual, Leon is like teaching us everything, as I explained. I think that have some ideas about it. But I want to make one final word, which is interesting about this. That Polyakov, in time writing Liouville, as Leon already explained, later, 6 years later, wrote something he called gravitational resonant working, which was Liouville, in kind of holomorphic way. What he did, he took a metric on Riemann surface, and of course he did Minkowski, and he called it dx plus dx minus plus h plus dx minus square. But we know what he meant is this. It is if I may, I would say he turned on the Beltrami differential, but not his complex conjugate. So he complexified mu and mu bar, okay? And he said I set mu bar to 0, but mu not to 0. And then he wrote an action which was equivalent to the Liouville action, called it gamma group. Equivalent in a sense that he said from the point of view of two-dimensional theory, one was just a conformal anomaly, another was a gravitational anomaly, and one can trade it one to another. So was this action, gamma of mu. And he wrote it also in terms of trivializing mu, writing mu as it's a -1,1 differential, so he wrote it in terms of certain scalar fix, there is a gamma of mu. Okay. So now, I would very like to say this on this conference because so many things get connected and there is the Young function and all these kind of things. I wanted to say that this particular action, gamma of f, has very nice interpretation in terms of, as was shown by Alexei and myself in 1988, in terms of another operator, b squared plus b, but now this is real. So this is now on a circle. So that b squared plus t that occurred, that thing was on a Riemann surface, okay, with some more punctures and so on. This is on a circle, and this action is something to do with the geometry action for field of constant. So somehow it's connected with us. Thank you very much.
We all have lots and lots of questions.
So you were very kind.
The two that he cut off. Well, we have the next speaker. So let's regroup in about 10 minutes. I have to go find them.